Hello, this is the first video of a playlist about the preparation of phenols. There's a PDF version of this presentation under the Community tab of my channel. Phenols are important target compounds and synthetic intermediates, but can be tricky to make. In this video we'll have a look at the preparation by rearrangement of benzylic peroxides, the cleanest and most relevant strategy. I've also included examples of Baeyer-Villiger oxidations and of the rearrangement of benzoyl peroxides. The second video of this playlist is about aromatic nucleophilic substitutions with hydroxide or alkoxides, and in part 3 we'll discuss electrophilic substitutions, for instance the direct electrophilic hydroxylation of unsubstituted arenes or the oxidation of metallated arenes. The fourth video is about aromatization by dehydrogenation or other eliminations and about ring-forming reactions. In part 5, I'll give you examples of some unique, mostly oxidative chemical transformations of phenols, including the dearomatization and dimerization of phenols. Because phenols are easy to oxidize, dearomatization or dimerization often occur as side reactions during the preparation of phenols. The best method for preparing phenols is often by chemical modification of another phenol. Phenols are highly reactive and undergo all kinds of aromatic electrophilic substitutions of hydrogen, for instance halogenation, nitration, and Friedel-Crafts alkylation or acylation. These reactions proceed under similar or milder conditions as with other arenes and are not discussed in this video playlist. I'll start this video with a short introduction about the general properties and uses of phenols. Phenols are much more acidic than aliphatic alcohols. Here you can see the pKa of some phenols, both in DMSO and in water. The pKa is approximately the pH at which a given acid will be 50% deprotonated. The pKa of unsubstituted phenol in DMSO is 18. 12 orders of magnitude more acidic than isopropanol. This high acidity is not caused by charge delocalization, but mostly by the sp2 hybridization of the carbon atom attached to the hydroxy group. Non-aromatic enols, for instance the enol of acetone shown here, are similarly acidic as phenols. Electron-withdrawing substituents, such as nitro groups, increase the acidity of phenols further. The nucleophilicity and basicity of the corresponding anions decreases with increasing acidity of a phenol. Unprotected phenols can tautomerize to cyclohexadienones. The ratio of phenol to ketone depends on the substituents and can also be influenced by acids and bases and by the solvent. Thus, phenols with electron-donating substituents at positions 3 and 5 show more ketone character because the keto form is stabilized electronically. Fluoroglucinol, for instance, the starting phenol of this example, often reacts as a ketone. Here, treatment with an excess of hydroxylamine yielded mainly a non-aromatic oxime. Fluoroglucinol can be prepared by alkaline hydrolysis of a triaminobenzene, as shown here. This facile hydrolysis suggests that 1,3,5-triaminobenzenes also behave more like an enamine or imine than like a fully aromatic aniline. Under forcing conditions, 1,3-dihydroxybenzene, also called resorcinol, can also react as a 1,3-diketone. Refluxing with an excess of sodium bisulfite for 4 days gave a high yield of a sulfite addition product. Alkaline saponification reversed the sulfite addition to the keto groups, and a 1,3-diketone resulted. The isolation and purification of sodium sulfonates is difficult and requires a lot of skill. Similar conditions also gave a low yield of sodium 3-hydroxybenzene sulfonate, again by bisulfite addition and hydrolysis. The energy required for cleaving OH bonds homolytically depends a lot on the other substituent at oxygen. Electron-rich phenols have relatively weak OH bonds, much weaker than that of water, carboxylic acids or aliphatic alcohols. Comparing these bond strengths with the CH bond strength of organic compounds shows that oxygen-centered radicals resulting from OO bond cleavage of alkyl or acyl peroxides will quickly abstract hydrogen from ketones, ethers, and particularly readily from benzylic or allylic positions. Elemental oxygen or phenoxyl radicals, however, are much less reactive and will not usually react with ethers or ketones. Particularly remarkable is the weak OH bond of the hydroperoxyl radical of only 208 kJ per mole. Thanks to this weak OH bond, the oxygen diradical is relatively unreactive, and most organic compounds, including us, are stable at the air and don't start burning right away. Toluene, for instance, is perfectly stable at the air because hydrogen abstraction by oxygen would require an energy input of 168 kJ per mole. Because of this low reactivity of elemental oxygen, the radical chain autoxidation of alkanes usually requires some radical starter, for instance UV light or strong heating. Unlike oxygen, however, peroxyl radicals are highly reactive and readily abstract hydrogen from benzylic positions, thus maintaining a radical chain autoxidation, as sketched here. Isopropylbenzene is converted into cumene hydroperoxide on an industrial scale by such an oxidation with air. Electron-rich phenols can prevent the autoxidation of alkanes by transferring a hydrogen atom to benzylic or peroxyl radicals. The resulting phenoxyl radicals are themselves unreactive and unable to regenerate benzylic radicals. Many important natural products contain a phenol substructure. Some of these are antioxidants, for instance gallic acid or tocopherol, but otherwise these compounds show a broad variety of biological activities. The function of morphine is to deter and kill herbivores. In humans, morphine mimics the terminal tyrosine of the enkephalines, which are involved in the feeling of pain. Death by an overdose of morphine is caused by suffocation due to respiratory depression. Because most phenols are easy to oxidize, during drug development, phenol replacements are sometimes required. Indoles can be suitable bioisosters but are also highly reactive. More convenient are therefore indazoles and benzimidazoles. Volatile phenols can have a strong, characteristic smell and are important flavoring agents. I've sketched here a selection of the most famous ones. Allylbenzenes are often mutagenic, safrole and methyl-eugenol for instance, but eugenol has not been classified as a human mutagen. Food companies and politicians often manipulate such decisions, and I would rather avoid too much spicy food. Plants are not concerned with promoting our health, but only with killing bacteria, fungi, herbivores, and other plants. Here are some valuable synthetic phenols. These include the anesthetic propofol, bisphenol A, a monomer for the production of polymers, and a number of biocides. As mentioned, volatile phenols can have a strong, not always pleasant smell. Some phenols are among the most intensely smelling compounds known, even surpassing thiols. Odor detection thresholds vary a lot from person to person and are therefore just indicative. As you can see from the values given here, alkyl phenols like cresol can be detected by humans at extremely low concentrations. If waste streams with such phenols are let into rivers, lakes, or the ocean, these phenols can accumulate in fish and render them inedible by spoiling their taste. Ethyl and propyl phenols have a particularly intense smell. The parent phenol is an important synthetic intermediate and is produced on a large scale, about 16 million tons worldwide in 2023. The main route to phenol is rearrangement of cumene hydroperoxide, the so-called Hock process. Smaller amounts of phenol are manufactured by oxidation of toluene to benzoic acid, followed by copper-catalyzed oxidation to salicylic acid and decarboxylation. Phenol is also obtained directly from coal tar. To put the amount of produced phenol into perspective, about 10 times more beer is brewed worldwide, and the total amount of crude oil produced in 2023 was 4,500 million tons. Thus, the amount of phenol is less than 0.5% of the amount of crude oil produced, most of which is just burned. Most phenol is used to manufacture bisphenol A, the starting material of various polymers, for instance polycarbonates, epoxy resins, and vinyl ester resins. 1/2 of the acetone obtained in the Hock process is used for producing bisphenol A. Then, reaction of phenol with formaldehyde yields bakelite, another important polymer. Phenol is also the starting material for many other products, for instance epsilon caprolactam, salicylic acid, diphenols, and various alkyl phenols. The main synthetic strategy for preparing phenols is from other phenols by aromatic electrophilic substitution of hydrogen. These reactions will not be discussed in this playlist. In this first video we'll have a look at procedures based on the rearrangement of benzylic peroxides. The other videos of this playlist are about substitution reactions that introduce the hydroxy group, about the dehydrogenation of cyclohexenones, and about cyclocondensations and cycloadditions. Benzylic hydroperoxides like cumene hydroperoxide readily rearrange to phenol and a ketone when treated with acids. This rearrangement proceeds particularly well with electron-rich arenes. One byproduct is acetophenone, formed when a methyl group instead of the phenyl group migrates to oxygen. Benzylic hydroperoxides are mainly prepared by autooxidation. Depending on the precise structure of the starting alkyl arene, such oxidations will proceed more or less readily. As an alternative, benzylic alcohols, ethers or halides can be treated with an excess of hydrogen peroxide. Another type of benzylic peroxide is formed when aryl ketones react with hydrogen peroxide. Again, acid-induced migration of the aryl group to oxygen leads to a new arene-oxygen bond. This is an example of Baeyer-Villiger oxidation. Similarly, benzoyl peroxides rearrange to aryl carbonates. I'll show you specific examples of these reactions later in this video. The Baeyer-Villiger oxidation of aryl ketones can proceed by various mechanisms, depending on the precise substitution pattern. With electron-rich arenes, a cationic intermediate can be formed, which then rearranges as sketched here. For less electron-rich arenes, the rearrangement may become a concerted process without cationic intermediates. If the R group migrates instead of the aryl group, benzoic acid esters will result as byproducts. Aryl groups tend, however, to migrate faster than simple alkyl groups. Let's check some specific examples. Baeyer-Villiger oxidation of a number of substituted acetophenones shows that aryl groups migrate more slowly when carrying electron-withdrawing substituents. 4-nitroacetophenone gave around 30% of the methyl benzoate, while methoxy-substituted and unsubstituted acetophenones yielded mostly the aryl esters. Too many electron-donating groups can be a problem though, because electron-rich arenes may also be hydroxylated directly under Baeyer-Villiger conditions. Here, oxidation of dimethoxyacetophenone yielded a hydroxylated aryl ester. Even anthraquinones can be converted into aryl esters. In this example, sodium perborate in trifluoroacetic acid brought about a twofold Baeyer-Villiger oxidation and the formation of an 8-membered phthalate. Again, the methoxy-substituted arene migrated first. Benzaldehydes are particularly easy to oxidize, but care must be taken to prevent the formation of benzoic acids. Benzaldehydes substituted with electron-donating groups often give high yields of phenols upon Baeyer-Villiger oxidation. Here, salicylaldehyde yielded catechol upon treatment with hydrogen peroxide under alkaline conditions. With catalytic selenium dioxide, even a tetramethoxybenzaldehyde underwent clean Baeyer-Villiger oxidation and yielded, after saponification, the expected phenol in 94% yield. In this example, an electron-rich benzaldehyde was oxidized with a slight excess of metachloroperbenzoic acid. Mainly the phenol and 2% of the carboxylic acid resulted. With unsubstituted benzaldehyde, however, the main product was benzoic acid. This is an example of conditions suitable for oxidizing isopropylbenzenes to hydroperoxides. Aqueous sodium hydroxide was the catalyst and air the oxidant. In this instance, a mixture of at least 3 products resulted. Treatment of this mixture with hydrogen peroxide and catalytic phosphotungstic acid gave resorcinol in 82% overall yield. As byproduct, some acetophenones were also formed. The Hock process can also be used to prepare other ketones than acetone. Here, sec-butylbenzene was first oxidized with pure oxygen and then cleaved into phenol and methyl ethyl ketone. Examples have also been reported of the rearrangement of electron-deficient benzylic hydroperoxides, as the one sketched here. The formation of acetophenones is, however, more likely here than with electron-rich hydroperoxides. Non-tertiary benzylic hydroperoxides can also rearrange to phenols, but more ketone will be formed as byproduct than with tertiary hydroperoxides. Here, the intermediate hydroperoxide was generated by stirring an electron-rich secondary benzylic alcohol with an excess of hydrogen peroxide and catalytic toluene sulfonic acid. No isolation of the peroxide was required because it rearranged as soon as it was formed. Like in the previous example, here a benzylic hydroperoxide was generated from a benzylic alcohol. Acid-catalyzed rearrangement in the presence of allyl trimethylsilane yielded an allylated benzopyrane. Similar reactions as the previous 2 examples can also work with oxone as oxidant. Here, with 3 equivalents of oxone, only 1 Hock-type rearrangement occurred. The product may, however, undergo Baeyer-Villiger oxidation, and it might be challenging to find the right amount of oxidant to prevent further oxidation of the product. Treatment of benzoyl peroxides with acids can yield aryl esters. Here, a mixed benzoyl peroxide, prepared from 4-phenoxybenzoic acid and MCPBA, yielded 4-phenoxyphenol as the main product when treated with triflic acid and then with potassium carbonate and methanol. Thus, again, the electron-rich arene migrated fastest. This example suggests that heating benzoic acids with hydrogen peroxide and a strong acid might yield phenols directly. I could not find any example, but if you know about any, please let me know. Non-oxidizable acids that do not react with phenols would be required, such as triflic or perchloric acid. On the other hand, sulfuric or hydrochloric acid would probably not work because sulfuric acid would yield sulfonic acids and hydrogen chloride would be oxidized to chlorine. So, what potential side reactions are to be expected? Phenols are easy to oxidize and an excess of oxidant should therefore be avoided. In the last video of this playlist, we'll have a look at the oxidative dimerization, dearomatization and ring cleavage of phenols. This here is a rather peculiar oxidative dearomatization of piperonal by phtaloyl peroxide. Here are some further examples which you can also find in the description of this video. The next video of this playlist is about the preparation of phenols by aromatic nucleophilic substitution, for instance by heating chlorobenzene with sodium hydroxide. See you there!